we're going.
Great. So, hi everyone. This is, I feel very excited about this lecture because this is the sort of the fourth, the fourth in this little mini series where we're building on the advanced we're sort of building on the sort of the basic core content, and we sort of started off with CNNs, and then friends did a great job with sequence to sequence and recurrent networks, and today we're going to sort of tail it off by talking about transformers, which have been really fairly breakthrough in some certain tasks. And also, in putting this lecture together, I realized there's a really nice story that you can kind of tell through the tension mechanism and addressing some of the issues that friends in particular raised last week. Okay, so let's begin. Yeah, so I want to be able to draw today. So where's the control gone? Oh, there it is. Great. Yes, so today we're going to talk about the transformer architecture, and in particular the attention mechanism. And so in many ways, I think you can draw a parallel between transformers and attention to AlexNet and convolutions. So when AlexNet came along as a network in 2012, it offered really attractive results on large-scale vision problems. Convolutions already existed as a mechanism, but really that was an architecture that brought all these things together, made some refinements with some breakthrough results. And I think you can paint a very similar picture here with what transformers are and what they mean for the landscape. And so specifically, attention already existed as an idea, as a mechanism. They refined it, they understood how to put it together, and then they applied it to NLP tasks, and they got really impressive results. And moreover, some of the insights that their results showed kind of drew light onto what the attention mechanism was able to do and not able to do, and then people have gone and sort of run along with it. The majority of the lecture is going to be about attention and transformer architecture and how it works and so forth, what sort of results it can give you. And so that's the first two. Where's my little cursor thingy? That's the first two bullet points you see there, and then the does everyone see this cursor? Where was I? And then the last two parts really are going to be extensions to transformers, where we kind of address some of the overheads of them. And then in particular, I want to be able to show you a couple of examples where people are using transformers for different tasks. So while they're similar to when I talked about CNNs, that was a lot of that was framed from the perspective of images and vision tasks, because that's where they've been so successful. Similarly, with transformers, the start of this, the most of this is going to be framed from the perspective of NLP tasks. Okay, So I want to connect to what Ferenc was saying last week, and so we learned about sequence-to-sequence modeling, and he talked to us about encoder-decoder style models, where you would feed in, for example, so you could have this encoder formulated as some recurrent network here, and then you had a decoder, again, some sort of recurrent network here. You're feeding an input, and it's internally building up state in the encoder that's eventually going to feed through to the decoder. And the job of the encoder is to sort of, in the case of maybe a machine translation example that he was talking about, you would have the words that are tokenized, some embeddings are generated, and then you feed these through as a sentence. You build up a what's called a context vector, and it's that context vector that is fed again into a decoder, where you're going to sort of take that context and unspool it for the translation, right? So that's we were there last week, and then if I move one slide forward, if I illustrate an Lstm here, I want to sort of work through this a little bit more, giving you more context, sort of kind of reinforce what he was saying, and then also to highlight a problem. So I was just saying how these an encoder and decoder, you could manifest these with lots of interesting neural mechanisms. So in this case, I've got an Lstm here that Ferenc brought up as he was giving us sort of his walk through recurrent architectures. And with this Lstm gating structure, you can imagine it being in the encoder here. And then as the inputs flow in, you'd have these words coming in, and it's building up this context vector that's going to be flowing into this long-term memory. So this it's a recurrent, right? So this LSTM cell is building up this state, and then it sort of winds itself up, internalizes the series of words that you can imagine as this fixed context vector. And then the decoder is going to do something similar. You could have a separate decoder LSTM that's been trained to consume in the long-term memory the context vector. The input to start it off is going to be some sort of signal to say, hey, start to produce this sort of translated state based on this context vector. And so it'll have the start symbol. It'll process the start symbol along with the context vector, and then unwind itself to produce the translation. But here's where we get to the problem. The problem is that this fixed context vector has to be selected at the start, and then in some sense it defines a maximum memory this model can have. And so you can imagine situations where you have longer and shorter types of sequences that might vary when you start to apply this. So in a machine translation case, you might have longer and shorter sentences. You might have a very long sentence or even a large passage that you want to translate. And then you have this fixed context vector that you need to kind of, that you'll have available to you to sort of internalize the state of the data that's being consumed. And so people realized that this was sort of a bottleneck in the process. And then as we move forward, to pick on a particular paper, around 2015, folks were thinking about, oh, this is not rendered properly. What if I hit return? Oops, sorry about this. Oh, it's still not good.
Can you zoom out maybe? Press minus?
Oh, you know what I'll do? I'll just... strange. Oh, strange. Anyway, let's just, I can tie the slides up later, but the point is, okay, yeah. The point is that in 2015, folks started to, oh, this is going to be a problem for the diagram, but let me just do one thing where I just, because I wanted to annotate this. Okay, anyway, let me just carry on. So I'm talking about in 2015, folks were realizing that the fixed nature of the context vector was actually a bottleneck in this process, in these sequence to sequence style models. And so what they wanted to do was, Banadu, and this was a Bengio paper, they wanted to investigate the context vector as a bottleneck and propose an alternative. And so they never used the word attention, or they used actually I looked in the original paper, they used the word attention only 3 times in the middle. But they proposed this technique that they called soft search. What they wanted to do was move away from having this fixed context vector to a process whereby they could have a much more dynamic context vector that can be that can grow based on the scale of the data that's coming into it. And I want to highlight it here. So in this diagram on the right hand side, we have the decoder. Here we have an encoder. We have oops, let me get the drawing mechanism going. Right. So this is a straight line. So this is an encoder. This is the decoder. This is the encoder. Remember, if we had in the prior design, all we'd have is the opportunity of presenting this final hidden state as a fixed vector to the encoder, right? And so then they said that this is a bottleneck. What can we do better? So instead, what they proposed is a system where you would instead consider all of these hidden states that accumulate as you put input through the encoder. And the way they did that is by presenting a dynamic context vector that ended up being the a weighted average of all other prior context vectors that are generated as you're passing data through the vector. And so you can't quite see the equations down here. But let me just, so the innovation here is the ability to have this weighting. And so this weighting allows them to have this mechanism they call soft search. And so what they're able to do is present through the context vector at each time step, capture the relationship that exists between the current time step and prior ones. And so that the mechanism works as follows. To get this, well, there's this equation here that essentially is a sum of the hidden states by some weighting alpha. Let me maybe I can draw it here rather than you can't see it. Okay, this alpha term. So it's the sum of this alpha term. Sorry, my drawing's a bit poor. Now the question is, where do they get their weights? So when you see the full version of the slide, you'll see that this weight is essentially, there's a normalization term here that you'll see. It normalizes the this weight, and then the key step is that they actually have a function that learns these weights by relating weight by hidden state going back through time to the prior state of the decoder. So I wonder how I could do this. Well, so imagine there's this function that's going to be a combination of the prior state of the decoder and each of the hidden states. Okay, and so by doing this, they're actually able to generate a context vector that's dynamic, that consumes and attends to the information not just at the final time step, but that's evolved through all of the time steps. And they're able to actually connect, the decoder is able to connect the state that it finds itself with all of the states in previously. Each the weighting that is available is connected to the state immediately previous in the decoder. And so through this mechanism, you've moved from a situation where previously it was just one single context vector that's always fixed to one that is now able to incorporate information through all the different time steps moving backwards. So if I just move, this slide didn't quite work out, but right, clear. Okay. So what were they able to achieve with this mechanism? So by introducing this level of dynamicness in the context vector, they were able to find that this relatively simple mechanism was able to learn very interesting alignments in the domain of translation. And so what we have here is an example through that mechanism of translating English to French. And so then in simple cases, we see that it learns that it needs to pay attention to one-to-one correspondences, for example, the and al, accord and agreement have very straightforward mappings. But the key here is that we want to be able to have the translation process realize that it needs to treat words differently based on the other words around it. So in some sense, it start to be able to understand the context in which a word sits changes the way it needs to be translated. And so what they discovered when they looked through this mechanism that it was able to learn very complicated relationships. So if we think about different languages, there are different orders of nouns and verbs and so on. And so in the simple example that's commonly examined, we can see that, for example, this translation of European Economic Area, the mechanism was actually able to learn that this order in translating from English to French needs to be reversed. So you can see that zone is so you can see that in the arrangement, the order is European Economic Area, but you can see here that the weighting applied is now allows for the reverse. And so this was already a big deal. By moving to more dynamic context vectors that consider this combination of the prior states rather than always trying to condense everything into one fixed vector, you're able to learn much more complex relationships. And so this is where the intention mechanism started and where the transformers really enter the picture. So if I move into the next slide, in this next stage, what the transformer paper really asks itself is a very interesting question. We have this situation where the encoder-decoder architecture is composed of recurrent cells of different kinds, and then they've introduced this new mechanism that allows it to have this dynamic context vector. And they ask themselves, in this relationship between those two types of mechanism, who is actually doing the heavy lifting? What is the key component that enables results that we just saw? And what they find is that the attention mechanism is actually doing the heavy lifting. It's the key part in being able to learn those types of relationship. It's not that you need the other mechanisms of recurrence and so on in that encoder-decoder structure. And so then they went ahead and ran with it and explored, well, what if we're right about this, what are we going to do and how are we going to leverage it inside an architecture? And this is where you get this well-known paper now, Ashwan and many others studying how you can, making this observation that attention is the key in performing this type of learning, and that you can do without the others. And because by doing without the others, you're actually able to make things far more efficient and still retain a lot of representational power. Oops. Okay, great. So because they realize that this attention mechanism is exactly what they need for doing this type of achieving these translation results, they actually presented and proposed a different formulation to the one that we saw, but it is doing a very similar task. So the reason that they want to do this is that, as we see in the coming slides, they're actually going to double and triple down on this technique. They're going to they want to simplify it because they want to reuse it throughout the architecture and have it be the key mechanism for doing the learning of representation. And so here we're just starting off by looking at it just from the perspective of a single element and calculating its relationship to some other adjacent element within a sequence. And so this will become clearer in the next slide. But what I want to do is just show it in isolation, whereby, let's see, I've got the drawing thing on. Yeah. Yeah, good. So we're going to see that we have an element that we're focused on processing. So this could be a particular word, concert or something. And then we're going to use this mechanism that's being illustrated here to compute pairwise with other elements the level of similarity of embedding between this word and another. And so we're going to have value be the current embedding, the current representation of that other adjacent element. And then we're going to use these two ideas here, these two concepts of query and key, where query and key allow these two things to be related. And so if you just look at this, this is a single formulation of attention between two pairs, where you could just focus on this query and key and consider that they're going to use this term here to allow sort of a cosine similarity understanding of the representation of the two elements that you want to consider how similar they are. That's why we use these two variables. And then once we have that as a weighting, we're going to multiply this by the value of the other element that you're considering. And this is the kind of key building block element. So if we move on to the, I guess what I'd mention, a key factor here is that we are using this to build relationships or understandings between other adjacent elements in a sequence. But unlike reoccurrence, we do not have any of this feedback within a cell. Right. So if you think back to, what's the alternative to having this mechanism? We could have some sort of recurrent network where we're going to have some state coming back in and of itself. And what that creates is a dependency that we can't really progress until we have this state being updated. It's a killer from being able to do anything in parallel. Whereas this mechanism, where we're making this observation of how similar it is to something else as the key building block, we can do all of these in parallel. So if this is the key building block for me to make a judgment between, say, one element and another, you can see that this building block can be done in parallel with many others. If I have a big long sequence of, 1 through 10 elements, I can have all of these comparisons being done at the same time, which is a big deal. So if I just clear this and move on, we can make this a little clearer. So in this diagram, we kind of see the full, I really want to present initially sort of a very zoomed in a view of this where you can just sort of focus on the raw building block. And then we can see it sort of more in action and sort of dive into how it's operating. So in this picture, let's make E2 the star. So we're going to use this new attention mechanism as a way to take its representation, and then at the start we're going to make a number of pairwise assessments of similarity between it using the mechanism we just saw, or this one that we see here. Right. So if we think of how E2 is some representation of a word, we're going to, in a sentence, we're going to look at making this comparison between the two of them. We're going to have value being, to start with, we look at performing the dot product between the two of them to make this comparison. This allows us to come up with a weight that you can consider a weight of like some sort of similarity between these words. We then allow the V. This is the representation of the current element 1 coming through. And then depending on this weight, so if they're very similar, we're going to, when we mix the two, we're going to really take a lot from the current representation of this E. If it's low, we're not. And then we do that for all in the sequence, right? So these could be, imagine we have a sequence of 4. We're going to do a pairwise comparison from E2 when we're computing E's new representation based on all of these, right? So we're going to do between E2 and E1, E2, E4, and so forth. Then these are summed together and then passed through a feed-forward layer that you could consider as being able to have the capacity to extract high-order features that can summarize what's going on. And this becomes the new representation of E2. So as I mentioned before, what's really important here is that you can perform all of these in parallel. The operations themselves are lightweight to compute. and yet we're still able to have this capacity to perform these type of sequential processing. So that's a key building block of this transformer architecture. And the next step to it is really a simple extension of it. What they consider is that in any sort of sequence, you can have different types of relationships that you need to be able to learn. And say if we just take the context of an NLP example, you might want to consider some sort of semantic relationship between the words that needs to be encoded. There could be those to do with connections between the words to do with who is doing what to whom. There could be similarities expressed based on words being of a similar category. So there could be words that are animals. These are all pieces of information that may be important when trying to consider a task like doing translation. Now, the current way, if this was our only mechanism, then you need to somehow have very different relationships be embodied in a single mechanism, right? So you'd have to have this comparison between these two. If you want to have the capacity to have different relationships represented, if we only present and encode in the model this type of a form, we're asking all of those different types of relationships to be sort of squeezed in to a single type of relationship. So what do? Well, and this speaks volumes to why they wanted to simplify the mechanism to start with, is because what they wanted to build. This one didn't render well either. But what they wanted to build was what they called multi-head attention. So they take this single scale dot product version of attention that was based on the original 2015 paper, but simplified so they could simply reuse many of them. And so it's to allow them to generalize this idea out, they parameterize the attention mechanism by adding these weights. So this equation here is a bit not rendered properly. I'll figure out why this has happened, and present you with the right sort of cleaner representation. But essentially, they have the parameters associated with each of these variables, so then they can have different versions of attention. And then they use these different versions of attentions and simply concatenate them and then weight those different versions of attention as needed for the task at hand. Now, the ways that they will parameterize the different versions of attention, they will define how different tokens or different elements should relate to each other based on different potential relations that exist. And this will be learned through the optimization process. Nothing is hand designed, of course. And then similarly, the importance of individual type of relationships that the multi-head attention may start to learn is then also weighted differently, right? So you might have a central key type of relationship that drives the execution of the task, that really is the most important factor, might be weighted more heavily than others. And then so I think if you were looking to make parallels with other architectures like CNNs, you could consider that in some respects, the individual heads of a transformer are really like individual kernels of a CNN. So while each kernel might perform a different type of role in processing an input, such as an image, these different heads might also perform a different type of role. And so it's important to be able to add this capacity within the architecture for it to be successful. So now here we've sort of arrived at sort of the architecture itself. On the right-hand side, we have the final transformer architecture that was proposed, where they had to sort of consider many factors for it to do well on its individual tasks considered. And on the left, I've illustrated the initial startings of the attention mechanism that had this idea of soft sort of a dynamic context vector that can consider sort of soft relationships in a much more richer fashion than your fixed context window. I wanted to sort of point out a few points about how the transformer architecture sort of functions. So let's see if I get this right. Okay, so then first off, we see our conventional encoder decoder architecture that we've seen before. We see the multi-head attention that I've been talking about thus far. And so we've seen this described a number of times. What's new that you haven't heard mentioned thus far is positional encoding. And so this is needed in the architecture because if you look at the attention mechanism itself, it does not consider position. So you'll get the same result if I go back a few, maybe I'll just go back a little bit. Yes. If we rearrange the order of these particular elements, because you're just doing a pairwise comparison, then they're not going to be sensitive to order. But of course, in tasks like sentence translation, order is going to matter. So in assembling the transformer architecture, they need to account for that. And so essentially to do that is a fairly simple mechanism. Alongside the representations that are included with each token are an additional, well, there are different ways to solve this problem, but essentially what they want to do is add a sequence that can identify the position of the word. And then essentially there are a lot of different mechanisms you can investigate to generate this sequence. But the key thing is that the sequence for one position should be different to another. And so by appending that sequence identifier, you could call it, with each word, then if, say, for example, words were to appear in different orders, their representation could be distinct. Or if two words appear in the same sequence, you could, the architecture is able to accommodate, understand this. So that's point number one. The other point I want to point out is a mechanism that friends introduced, I think, in the last lecture. This idea of residual connections, and so we can actually see them appear here in the architecture. And I think these are all these points here, like this positional encoding, the appearance of residual connections, and so on, is at least from my point of view, a really nice sort of insight into the nuts and bolts that are necessary to have a successful architecture perform the task that you want to perform well. So one main motivation for them including these types of residual connections that allow the signal to also pass through is that what they found is that if they did not include these, the architecture would start to ignore the positional encoding. And that's because that the attention by itself, and attention is the only mechanism we have at work here, is unable to identify these different orders. And so when they don't have these in the architecture, then they find that the positional encoding just disappears. So by allowing these by including these, they find that positional encoding is maintained. That's one of the reasons why they add them in. And then getting back to the actual functioning of the architecture, it'll operate very much in the same fashion we've seen in other encoder-decoder style. We have the inputs fed in. I've mentioned about this embeddings, but essentially rather than present, in the case of NLP, to actually have these things, have this sort of task be performed, you will take words, tokenize them into individual units, and then project them into an embedding that gives them sort of a broader it allows them to be represented in a richer way where they're already related to each other. So there are many different ways that you can embed a word that sort of tries to include its semantic, but word to vec is a very common embedding. But essentially, you need some sort of embedding that allows the raw token to be represented. The encoder will generate the different type of context vector that is then fed into the decoder. To do the translation, you'll present to the decoder phase a start symbol, and then it'll start to produce the translation by using the context from the encoder and so on, just as we've seen before. Okay. So after they're assembled, the real kind of punchline to this is that once they investigated, again, looking at this paper, once they investigated what is doing the heavy lifting, okay, looks like attention is doing it. Okay, if we're going to lean so heavily on attention, let's make it simple. Okay, now let's try to make an architecture built around attention to sort of emphasize its strengths. Then what can it deliver for us? And what it could deliver in this paper was really results that made a lot of people sit up and look at what this mechanism is able to do. And so what do we see here? This is for a language translation task. And so we're in this way of scoring English to German or English to French, higher numbers are better. And then what I really appreciate about this plot, this figure, is that it also includes the floating point operation. So this is a comparison of the transformer architecture doing this task against a variety of alternatives. And then you can see, this, big jumps, big reductions in the amount of floating point operations required to learn this architecture. So this architecture is comparatively cheap. It's very cheap compared to other types of recurrent networks and other styles of learning the same problem. And yet it's also able to deliver very high scores. And so you can see that it's actually dominating other types of approaches here. So it's proving to be very useful and very cheap at the same time. Not only are the number of operations lower, but as I pointed out before, they are much more able to be executed in parallel, which is another important dimension to this. So this was a big sort of breakthrough that people really started to think of, like, how can they use this type of mechanisms in other tasks and so on. So now we've got to this exciting point that we now understand what transformers are and so on. I wanted to sort of use the remaining time just to point out some of their weaknesses. For example, now that we've got this, there's no free lunch in life. Now that you've introduced a new mechanism and architecture and so forth, where are the bottlenecks starting to appear, and where have those bottlenecks started to be refined? And so I think, given the time allowed, remaining. I want to be able to, I'm going to cover two of these extensions so you can kind of see this at work. And then I want to briefly cover at least this image-based example, because I think this is when we start to see this potential shift of broader applications of transformers that is starting to appear. So when you start to use transformers and start to scale them up, one place that you see bottlenecks appearing is in the sequence length. So if we go back all the way to probably my favorite slide, the one that wasn't ruined, this one, this illustrates for us why we're going to have eventual bottleneck. We've got some really nice capabilities. It's a lot simpler, as I mentioned, in two other recurrent networks and so on. But it's this pairwise thing that's going to eventually kill us. If we have a small number of sequences, we're going to be okay, right? Pairwise is not going to be so good, not to be too bad. But as we have certain tasks where the sequence needs to get bigger and bigger, we're going to face this quadratic complexity because of all these comparisons. And that is, so it's like any optimization problem when you're trying to speed up the computation. You might remove a few bottlenecks, and as you start to make this thing bigger and bigger, you just have other bottlenecks appear. So the first two papers I'm going to talk about really a look at, well, what can we do with this complexity that comes from the sequence size getting bigger. So if I just hit this button, actually, yeah, perfect. The first of these is a really recent paper. So we've if you think about also mentally where we've come from, so 2015, there's a new mechanism. It's not even called attention, but it has the building blocks that when in 2017, people started to look at what it could be used for and realized just how powerful it was. They could simplify it and build a whole architecture around it that really leans into its benefits. Then here we have papers in 2020 that are looking at, okay, what are the remaining bottlenecks? Oh, okay, we've got this quadratic complexity given the sequences. What can we do about that? And so reformer actually is a style of transformer that has some really simple ideas that are able to sort of bash down this complexity down to more logarithmic as the sequence grows. So how do they do that? Well, everything you need to know is illustrated on this left-hand side. They take the sequences and they use hashing to come up with a bucketing for them, right? So that's what you see here. They're being color coded. Once they're now bucketed into a few number of bins, then they can be ordered. And once they're ordered, they then can be chunked into different chunks based on a clustering of their buckets, right? So you can see this happening. And then, so why are we doing this? The reason why we're doing this is simply because we want to reduce the amount of comparisons that are needed during the attention mechanism. And so that's what they do. Once they have this sort of arrangement of the data performed, then they are no longer performing n by n comparisons. They're now only comparing within these clusters. And so they're limiting the kind of capacity of the network to afford better scalability. And then they make a few concessions, which is namely they allow comparisons between these clusters based on the hashing. And so you can see this happening in the illustration. So it's a very sort of simple staging of this approach to kind of extend the existing architecture to allow it to scale better. And then, so these are results. The important thing that you want, where they compare an off-the-shelf existing transformer to this sort of proposal. And so what you really hope to see from results of this type is what you see, I guess, let's point out the results on the right-hand side. You would hope to see that as you, and this is the loss, as you're training large amounts of data, and you'd want to see that the behavior of the two architectures, the one where you have modified it, you've in some sense debilitated some parts of its capacity to learn certain things, but at a benefit of the complexity. And so what do we see? We see exactly what you want to see. They're behaving roughly the same. Where I would point out that they call them, it's called reformers, but on the plots they also like to call themselves reversible. And so the next example follows in a very similar fashion. I just want to quickly sketch it out for you. It's called a lymphoma. Again, they're going to really fight against the sequence-based overhead, but they take a different approach. Essentially, what they observe is that if you look at the attention mechanism, I'll just sketch this out for you very quickly, and they look at the matrices that are described by the attention mechanism, they find that they can be reconstructed very faithfully by a few number of eigenvalues used if you decompose the matrix into eigenvalues based on something like PCA or so on. And that's what these figures are showing us below here. They're saying that if we have a much larger matrix that is used to describe all these different types of relationships, right? You can have a larger matrix that encodes all these different pairwise comparisons, all these comparisons that you're doing between different terms, and you look at the information that is contained there. Well, then this figure is saying that for about, I don't know, with say for 128 of these eigenvalues, that a small fraction of the total matrix, I can reconstruct from these, very faithfully up to 90x the total matrix itself. And so they do this analysis that says, hey, this is possible. All these matrices are actually low rank, and so we actually could apply some of these linear algebra type of solutions to allow us to control for this complexity. And so once they make this observation, the change is very small. And so the change that they simply do is shown here. So I could describe this in two sentences. They insert a new component in the architecture that's going to perform a projection. And so when you're calculating these V and Ks and doing this sort of comparisons, as you might grow the number of sequences larger and larger, when it comes time to do these comparisons, you first project down into a smaller matrix. And so the key question is, well, how you do this projection and so forth. And what they do is actually just structure it within the learning. They set it up so you can actually learn this projection straight from optimizing for the loss. And so they don't have to really worry about how am I doing it and so forth. They learn it straight from the training data in terms of a successful projection that's going to allow them to still have high levels of accuracy, but without this sort of issue of as they increase the sequence length, these numbers these sizes are going to increase, but because they're projecting down, they can control for that. And that's what you see happening on this right-hand side. So let me just quickly get to the end so I can kind of wrap this up a bit. Up until this point, this has been sort of a discussion of a really promising new mechanism that's made big strides in the area of NLP. But if you fast forward again, so we talked about two papers that from 2020, let me tell you about another paper from 2020. And this is a paper, again, very new. Now that you know the transformer architecture, how it works will be very familiar to you. We don't have the objective is to show that transformers can be successful in a very new domain to them, those of images. We want to be able to do image classification. And then before they came along, the way that you would definitely want to try to do this is with CNN, what we talked about, I guess, at the very start of this little extension from the core series of lectures. But what did they find? They found that transformers could be a very promising approach for performing these types of tasks as well. How do they do it? Well, it's very straightforward. They take the image, they break them down into little patches, as you can see being illustrated here. These can be treated as words. We've been talking about words being flowing into the transformers this far, so you can treat each patch and linearize it and call this a new element. Then you'll feed into your transformer each of these different elements of the image. And we just want to do a classification. So what we can do is that we can forget about having this encoder-decoder style of arrangement of an architecture, and instead just use a single transformer to act as an encoder that we've seen before. And instead of feeding information into a decoder to produce some sort of translation, we're just going to have an MLP, right? So just a simple classifier at the end to determine what sort of class we have in the image. So what we've done here is just come up with a formulation of using a transformer to perform this image task. But what is really interesting is that once they did this, and they looked to see what it was learning. It was learning very reasonable things. You can see this. This is just a series of illustrations where you have the input image, and you can see the what the attention mechanism is learning to kind of consider collectively when it's trying to make its decision. So if the task here is doing object classification, you're trying to classify the sort of dominant object within the image. You would hope that if I was trying to realize this as a dog, I would sort of look at a lot of the pixels that relate to this single object, and you can see that this is what it seems to be doing. And then, so what do they find? They find that a transformer is actually able to set new state-of-the-art results beyond the existing CNNs. And so this is a really interesting indication of where things are going. We have a cheap to compute powerful mechanism that in one domain, in the domain where it's dominated by sequences, it does really well. Then we take it into a new sort of area where we've got an existing style of architecture that's been very successful for very, very long. And then what do we find is that by careful construction of the architecture again, we're able to exceed the results of the CNN. Now, there's a couple of prefaces that I need to make, though, to achieve this. And so this is the results that got people's attention. When you have results like this, if they're in bold, it means that they're the dominant figure across any other type of comparison. And this is comparisons against, for example, ResNets, and this is a efficient net using additional data. The thing, so number one is, hey, look, transformers are able to do extremely well in terms of accuracy, beat existing CNNs. The thing I should point out that they're only able to do this when they're actually pre-trained, so seeded with a huge amount of information. So Google has internally a labeled vision data set of 300 million images, so something that can actually dwarf that of ImageNet, which is what typical sort of academics play with. They're only able to achieve these results when they expose the transformer to this huge amount of data initially, and then fine-tune it for the specific task they want to do well in. But I think in time, like many of these cases within this area of deep learning, we can once we have results of this that point us in the right direction, then a lot of people can pile on to understand how we can start to make efficiency gains or smarter decisions about architecture design and so forth to really push these sort of numbers forward. And so I guess I really wanted to sort of close. I do have another example, but I just want to close by just wrapping this up, saying how transformers have really presented sort of an Alex ImageNet like moment in the context of NLP tasks, where we have this design of a mechanism that's relatively lightweight, but is able to kind of capture the types of relationships that we need, and by having this lightweight mechanism, we're able to scale up the architecture by going to, for example, these multi-head, deep types of transformer architectures. And then what's really even more exciting is that now we're starting to see that these architectures are also successful for other tasks that we already knew how to do, but they can do them better. And so, time will tell. I guess Neil and friends might want to weigh in about where they might see things moving in the future. But I think this is really sort of a lecture that's sort of poised to see where things will go moving forward. So that is 3 o'clock. I'm happy to take questions.